Hello, my name is Hassan Dabaja. I'm from the Laboratoire d'Informatique et des Systèmes, LIS, at Aix-Marseille University. I'm going to present my paper, Non-Destructive Testing in Structural Health Monitoring, an overview. This paper is presented at the 9th International Conference on Control, Automation and Diagnosis. Of the presentation is as follows. Introduction, ultrasonic testing, magnetic particle testing, eddy current testing, radiographic testing, and acoustic emission testing. Then we will end with a conclusion. Let's start with the introduction. We will do a comparison between the traditional method, which is visual inspection, and non-destructive testing. Visual inspection identifies surface defects. It's simple and inexpensive. It provides immediate results. It is limited to surface defects. It can be subjective and it only works in accessible areas. On the other hand, non-destructive testing detects degradation, damage, cracks, and abnormalities. It does not cause damage to the material, and it can detect subsurface defects. It requires specialized equipment and expertise. It can be time-consuming, and it's limited when it comes to inspecting complex geometries. Non-destructive testing have the following benefits. It reduces the risk of failure. It extends the structure's lifespan. It lowers the risk of accidents. It protects human life and the environment. The limitations of non-destructive testing, on the other hand, are the following. It's limited when it comes to complex structures. Manual inspection can cause costly performance interruptions. It's difficult to access internal and non-visible parts. It's more suited for simple structures than complex ones. Structural health monitoring offers real-time monitoring of structures. Non-destructive testing is typically deployed to further assess any detected anomalies. For example, structural health monitoring systems can monitor stress levels in bridges, and when potential issues arise, non-destructive testing methods like ultrasonic testing can examine specific areas more thoroughly. Roles of non-destructive testing in structural health monitoring. It accurately detects small-scale damage, and it helps in preventive maintenance. There are several applications of non-destructive testing in different industries. In aerospace industry, non-destructive testing detects cracks in turbine blades, fuselage, wings, and landing gears. In automotive industry, it inspects welds, engine parts, brake systems, and tires for defects. In construction, it evaluates concrete, steel structures, welds, and aging infrastructure. In power generation, it checks boiler tubes, turbines, and piping for corrosion, wear, and stress. In manufacturing industry, it detects flaws in metal casting, welds, additive parts, and electronics. In shipbuilding, it inspects hull welds, propellers, rudders, blast tanks, and onboard piping. In railways, it examines rails, wheels, axles, and infrastructure for cracks and integrity issues. In nuclear industry, it monitors reactors, piping, fuel rods, and containers for damage and leakage. We will start with ultrasonic testing. Ultrasonic testing uses high-frequency sound waves to examine structural integrity. It can identify voids, fissures, and differences in thickness. A probe emits high-frequency sound waves into the inspected material. These waves travel at a material-specific speed and reflect back to the probe when they encounter a surface or boundary. In the absence of defects, the waves pass through the material uninterrupted, reflecting off the back surface and producing a single signal on the display screen. However, if there is a defect, the waves will reflect off the defect before reaching the back surface, resulting in an additional signal. This allows the detection of flows within the material based on the reflected signals display. Shirahata et al. Applied ultrasonic testing to detect fatigue cracks in steel bridges. Their focus is on the flange ghost weld joint and successful detection of small cracks. Young et al. Discuss ultrasonic detection methods for mechanical characterization and damage diagnosis in advanced composite material, noting the typical damage types and the challenges posed by complex acoustic wave propagation. Mura et al. Discuss the use of ultrasonic testing for evaluating the residual compressive strength of concrete after high temperature exposure. We will move to magnetic particle testing. Magnetic particle testing is mainly used for inspecting ferromagnetic materials like steel by applying magnetic particles to the surface. This method is commonly employed in detecting surface cracks in welded components. When ferromagnetic components are placed in a magnetic field, any surface or subsurface discontinuity perpendicular to the field generates a strong magnetic leakage field. This field attracts ferromagnetic particles to the discontinuity location, creating visible indication of flows. Zulfagari et al. Evaluate the reliability and sensitivity of visible magnetic particle non-destructive testing for detecting surface cracks in welded components. Ueda et al. Develop a deep learning-based segmentation algorithm for defect detection in magnetic particle testing images, enhancing automation by improving defects identification in complex inspection scenarios. Wu et al. Present a deep learning-based framework for automated crack detection and 3D localization using fluorescent magnetic particle inspection. Now we'll discuss eddy current testing. Eddy current testing uses alternating current in a coil to create a magnetic field, inducing eddy currents in a conductive material. Defects in the material disrupt these currents, detected by a sensor. It is applied in sorting materials, detecting corrosion and cracks. It helps finding flaws in metal without causing damage by analyzing disruptions in induced electrical currents. Mohseni et al. Comprehensively explored the reliability of manual and automated eddy current testing scans for surface fatigue cracks detection in aerospace structures, highlighting the importance of probability of detection studies. In Yu Chanin's research, advanced eddy current testing techniques were implemented for the timely detection of surface breaking fatigue cracks and corrosive damage in aircraft structures. Now we will move to radiographic testing. Radiographic testing uses radiation such as X-rays or gamma rays to create images. The radiation is absorbed depending on the thickness of the material. As the radiation passes through an object, it gets weaker, especially in areas with structural changes. Cracks, which block radiation, show up as lighter areas, while denser parts appear darker. The resulting picture showing the changes represents a flat view of the radiation. A computer vision algorithm is used to analyze the image for damages or irregularities. Yahagi et al. Proposed a three-step methodology employing wavelet denoising, shape from shading, and the Harris corner detector for enhanced defect detection in radiographic images of welded objects. Tis Jarvi et al. Applied advanced deep learning techniques, including virtual flow augmentation, to improve the efficiency and reliability of radiography-based non-destructive evaluation in the aerospace industry. Moving to acoustic emission testing, stress changes within a structure due to reasons such as corrosion, fatigue, or impact cause it to emit detectable acoustic waves. Acoustic emission occurs when a material fractures, releasing stored strain energy. This energy release causes the nucleation of cracks and generates AE waves. These waves propagate through the material and are detected using AE sensors. The sensors are typically piezoelectric elements attached directly to the material's surface. When acoustic emission waves reach the sensor, the dynamic surface motions are converted into elastic signals, allowing for further analysis and interpretation. Acoustic emission is widely used for real-time monitoring of structural integrity in various industries. Applications include large-scale structures, pressure vessels, pipeline, bridges, storage tanks, and large low-speed bearing. Let's conclude our presentation. This overview elucidates the operational principles and applications of key non-destructive testing techniques. Non-destructive testing is important in inspecting and monitoring the health of structures. They are components in several fields such as aerospace, automotive, construction, and power generation. They play a significant role in spotting problems and reducing the occurrence of dangerous accidents. The techniques discussed in this paper are ultrasonic testing, magnetic particle testing, eddy current testing, radiographic testing, and acoustic emissions. Future work may discuss these techniques in terms of cost, sensitivity, and limitations in real-world scenarios. Thank you very much for your attention.